this way, we have defined the poles and residues. Residues are for single poles or for multiple poles. Now let's solve the problems. For example, suppose we have a complex function like this. First, we have to find the poles of the function. And they say that is a triple pole here. And that equals to 0 is a triple pole. That equals to 1 is a single pole. So we can easily find the residues for these 2 points. First, we can declare the origin variable z and then express the original function. And then for z equals to 0, we have to process it with a multiple pole formula. And we have f times z to the power of 3. Take the second order derivative and divide it by the factorial of 2. And then we take the limit to let z equals to extend 10 to 0. We can find the residue at this point. And also because this one is a single pole, we can use this formula, this command, to find the second residue of the system, of the function. So these are the 2 residues. One is for z equals to 0, where it is a triple pole. And for the other one, z equals to 1, we have a residue like this. So we can use these 2 values to replace the original function at these 2 points. Now let's consider what is the poles and what is the multiplicity of it, and then what is the residue of it. It seems that the residue of the multiplicity of it is 6 at z equals to 0. So we can solve the problem easily by commands like this. This follows exactly the one I have listed in the previous slide. We can find finally the residue is 1 over 120. So we can easily calculate the residue of the function. So now our question is, what is the actual multiplicity of the pole? If we do it by hand, we will see that the Taylor series of sine z is something, I'm to write it down on the slide. Z is sine z is z minus, I'm not quite sure of it, something like this. And you can cancel this term to minus z, and they leave the rest of the polynomial with cube, z cube. We can cancel that one with z to the power of 6. So the actual multiplicity of the pole is a triple pole. So how can we find the exact value of multiplicity? The idea is that we can try different multiplicities from 1, 2, 3, and so on, and find which of these, if you use multiplicity 1, 2, 3, 4, and so on, using this kind of formula, see which multiplicity will give you a finite R. If for a certain value you can get the finite value of R, then we say that the value is the multiplicity of the function f. Display it later on to you. If we have 2 here, we have 1 here. 1. Which means means that we are trying the multiplicity of 2, and we see that the result is NaN. If we try 2 here, so I made a mistake here. You have to use that to the third power here for multiplicity of 3, and we can find the residue, which is finite one. So we say that the multiplicity is 3, which is exactly the same as the one I analyzed by hand. So in this way, we can try different value of k here and see which one will give a finite number r, and then we can say that the multiplicity of it is the number there. And it is also very interesting to note that if I assume that this pole has a multiplicity of 6, that gives a residue of 120, 1 over 120, which is the same as the one here. So what if I try large numbers? So for instance, we try 20 here, and 19 here, we should get the same result. And from computation point of view, the multiplicity of the pole is not very necessary. We can use a large number. They will always give the same residue, whatever you use. Suppose the value here is larger than the actual multiplicity of the function. So we can try different values for k here. K2 means that the result is not a number. And if k equals to 3, we can get 1 over 120, and so on. And now, how can we calculate the residues of the function? Like this. And before that, we have to find the poles and multiplicity of the poles. We will see that z equals to 0 is a pole. And besides, what makes this part 0, sin z equals to 0, k times pi. Yeah. So if z equals to k times pi, then the denominator will be 0. So it is also a pole to the function. And z equals to 0 is a special case of it, when k equals to 0. However, it must be noted that if k does not equal to 0, and equals to 1, which is a single pole. If k equals to 0, we have a double pole. Right? So these are the multiplicity of the poles. And how can we define the integer k here? There is no way under Maple or the symbolic toolbox we cannot define an integer. So we have to try different values. For instance, k equals to 1, minus 1, 2, and minus 2. Try several numbers and see whether you can get something with a certain formula. So for z equals to 0, we can easily find the residue of it because it is a double pole here. So we have to use this command to find the residue of it. And the result is 0. And for z equals to plus or minus k pi, where k does not equal to 0, we have to try several values. For instance, k equals to 1 minus